These solar storms, with their coronal mass ejections, are responsible for the Aurora Borealis, or northern lights, and the Aurora Australis, or southern lights. Here's a look at the Aurora Borealis and Aurora Australis taken from the space station. The aurora lights were a mystery for most of man's existence. It wasn't until our modern understanding of the magnetosphere via satellite observations in the second half of the 20th century was combined with quantum mechanics developed in the first half of the 20th century that a real understanding was reached. What happens is that the magnetosphere routes the solar wind charged particles along the Earth's magnetic field lines to the north and south polar regions. There, they collide with oxygen and nitrogen atoms in the thermosphere. Quantum mechanics explains how these collisions create light. I'll take a minute to explain this because it's relevant for understanding how a star's light can tell us how far away the star is. Thanks to the work of Niels Bohr, a Danish physicist, we discovered that electrons attached to atoms occupy quantized discrete energy levels called shells. The further the shell is from the nucleus, the greater the energy level and the larger the quantum number. And thanks to Albert Einstein, we discovered that light was also quantized as photons, and that they were created when electrons drop from higher to lower energy levels, sometimes referred to as taking a quantum leap, and absorbed when a photon collides with an atom and drives an electron to a higher energy level. In the case of the aurora, the high-velocity particles from the solar wind collide with the oxygen and nitrogen atoms in the thermosphere, driving electrons in those atoms to higher energy levels. When they drop back down, photons are created. For oxygen emissions, we get mostly green light, the most common auroras. From nitrogen emissions, we get mostly blue or red. We'll go deeper into quantum mechanics and light at the beginning of our segment on distant stars.